Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. The word stress means a change in concentration, pressure, volume, or temperature. Click on one of the buttons below to view animation showing the effect of these stresses on a system at equilibrium. Iron 3-thiocyanate, which is FeSCN3, dissolves readily in water to give a red solution. The red color is due to the presence of hydrated iron thiocyanate ions, FeSCN2+. The equilibrium between undissociated iron thiocyanate ions, iron 3+ ions, and thiocyanate ions SCN- is given by this chemical equation. FeSCN2+ aqueous, which is red, in equilibrium with iron 3+ ions, which are pale yellow, plus SCN- aqueous, which is colorless. Click on one of the buttons to add sodium thiocyanate or remove iron 3+ ions from the solution. In this case, the stress applied to the equilibrium system is an increase in the concentration of thiocyanate, SCN-, from the dissociation of sodium thiocyanate. To offset this stress, some iron 3+ ions react with some of the added thiocyanate ions, and the system shifts from right to left to re-establish equilibrium. When the system shifts to the left, iron thiocyanate ions are produced, which have a red color. Consequently, the red color of the solution deepens as more iron thiocyanate ions, FeSCN2+, are produced. Note that the sodium ions are not shown in the simulation because they are spectator ions. Oxalic acid ionizes in water to form the oxalate ion C2O4 which binds strongly to the iron 3+ ions. Free iron 3+ ions are removed from the solution as the stable yellow ion iron 3 oxalate is formed. The system shifts from left to right to replace some of the iron 3+ ions. As the system shifts to the right, the concentration of iron thiocyanate ions, FeSCN2+, decreases. The red solution turns yellow due to the decrease in concentration of the red iron thiocyanate, FeSCN2+ ions, and the formation of the yellow iron 3 oxalate ions. Note that the reaction between iron 3+ ions and oxalate ions is not shown. The shift in the equilibrium position is the focus of the simulation. Consider the equilibrium between iodine gas molecules, I2, and iodine atoms at high temperature. Iodine molecules in the gas phase are a purple color, and iodine atoms are colorless. Under the given reaction conditions, the ratio of I2 molecules to iodine atoms is 2 to 3 at equilibrium, as shown in the microscopic view. Let's stress this system by changing the pressure. Click on one of the pressure buttons. You have increased the pressure by decreasing the volume of the container. The system can partially offset this stress by decreasing the moles of gas. Recall that pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, the moles of gas can be decreased if the system shifts to the left, producing iodine molecules and decreasing the number of iodine atoms, as you can see in the microscopic view. As more iodine molecules, which have a purple color, are produced, the color of the equilibrium mixture darkens. This can be seen in the macroscopic view. Note that the total number of gas particles has decreased from 10 to 8. You have decreased the pressure by increasing the volume of the container. Le Chatelier's principle states that this stress will be partially offset. The system can partially offset this stress by increasing the moles of gas. Pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, more moles of gas can be produced if the system shifts to the right, producing more iodine atoms, as you can see in the microscopic view. As more iodine atoms, which is a colorless gas, are produced, the color of the equilibrium mixture lightens, as you can see in the macroscopic view. Note that the total number of gas particles has increased from 10 to 12. Consider the following reaction at equilibrium. N2O4 in equilibrium with nitrogen dioxide, NO2. Under the given reaction conditions, the ratio of N2O4 molecules to NO2 molecules is 2 to 3 at equilibrium, as shown in the microscopic view. Because NO2 is a brown gas, the equilibrium mixture has a brown color, as shown in the macroscopic view. Let's stress this system by changing the temperature. Click to select either increased temperature or decreased temperature. You have increased the temperature of the system by adding heat. The Chatelier's principle states that this stress will be partially offset. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can partially remove the added heat by shifting to the right, producing more NO2 and decreasing N2O4, as you can see in the microscopic view. As more NO2, a brown gas, is produced, the color of the equilibrium mixture darkens, as you can see in the macroscopic view. You have decreased the temperature of the system by removing heat. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can replace some of the heat that was removed by shifting to the left, producing more N2O4 and decreasing NO2, as you can see in the microscopic view. As more N2O4, a colorless gas, is produced, the color of the equilibrium mixture becomes lighter, as you can see in the macroscopic view.